Hello again. In this video, I'm going to go over this homework problem from 311. So let me read through it and I'll show you how to do it. So it says a piston is seated at the top of a cylindrical chamber with radius 2 centimeters when it starts moving into the chamber at a constant speed of 5 centimeters per second. What is the rate of change of the volume of the cylinder when the piston is 20 centimeters from the base of the chamber? Okay, so this is called a related rates problem. And so in this particular problem, there are different rates of change that are given to us, and there's a certain rate of change that we're trying to solve for. And then what we're going to do is we're going to come up with an equation which describes the relationship between those different rates of change. So what I suggest that you do in a related rates problem is to first write down those rates of change that are given in the one that you're trying to find. Okay, so reading through this problem, you can see we're trying to find the rate of change in the volume of the cylinder, presumably over time, when the piston is 20 centimeters from the base of the chamber. Okay, so in terms of a rate of change, rates of change are derivatives. Okay, so this rate of change, we're looking for the rate of change in the volume over time. So that would be dV dt, the derivative of the volume with respect to time. And we want to find it when I'm going to call this the height, the distance from the bottom of the cylinder all the way up to the top of the piston. I'm going to call this h for the height. Okay, and we're supposed to find the rate of change in the volume over time when the height of the piston is 20 centimeters, right, as measured from the base of the chamber. So we're going to evaluate this derivative when h is 20. And that's what we're trying to find. That's the rate of change that we're looking for. Essentially, this derivative evaluated at h equals 20. Okay, so that's the rate of change we're trying to find. And then if you read through the problem, we're also given one of the rates of change. If you notice here, it says it starts moving into the chamber at a constant speed of 5 centimeters per second. Well, that's a rate of change. Okay, in fact, so that they're telling us that this little circular piece is moving into the chamber at a rate of 5 centimeters per second. Okay, as that happens, the height of the cylinder is decreasing, right? And so that means the height is decreasing at a rate of 5 centimeters per second. Okay, so that's dH dt. That's the rate of change in the height of the cylinder over time. And one thing you should take note of is the height is decreasing over time, so it's losing 5 centimeters every second. So this should be a negative rate of change. And take note, this is constant, this rate of change. Okay, regardless of what time you're looking at the cylinder, the rate at which this little circular piece is moving into the chamber is always 5 centimeters per second, and of course it's negative because you're losing height. Okay, so these are the rates of change, right? This is the one we're trying to find, and this is the one that we're given. Okay, and so what you should do next is try to find an equation which would describe these two rates, right? How they're related. So what we're actually going to do is we're going to relate volume to height first. We're going to try to figure out a relationship between volume and height. And we know that. The volume of a cylinder is pi r squared times h. Okay, so this gives us a relationship between the volume and the height. And then what we're going to do is we're going to take, I call this like the foundational equation. You should always start with your foundational equation. And then we're going to take the derivative of this equation with respect to time to get the two different rates we have here. So I'm going to take the derivative of both sides with respect to time. Okay. Okay, so this left-hand side, that's just dv/dt. Okay, and then on the right-hand side, we're going to find the derivative of pi r squared times h with respect to time. Now notice pi is a constant, and you can pull constants outside the derivative operator. So I'm going to pull that out. And then we have to find the derivative of r squared times h. Now in order to find that derivative, we're going to have to use the product rule because this is the product of two different functions. Right? R squared is the first function and h is the second function. Okay, so using the product rule. Now remember the product rule says you take the first function, which in this case is r squared, and you multiply it by the derivative of the second function. Of course, the second function is h, and you're taking the derivative of that with respect to time, so you just get dh dt. Okay, so that's the first times the derivative of the second, plus the second function, which is h, and then times the derivative of the first function, which is r squared, or the derivative of it is the derivative of r squared with respect to time, right? So we have to find that derivative. Now I'm going to find this derivative on the side, okay, because it's kind of unique. Presumably r is a function of time, okay, and we're taking the derivative of it with respect to time, okay, and then this radius is being squared, right? You have r squared. So this is really a composition of two different functions. There's an inner function, which is r, that's a function of t. So that's your inner function. And then your outer function is like a squaring function, right? You're kind of squaring it. So if you want to write this as, you could think of it as like f of x is x squared. That's your outer function. Okay, but this r squared is really a composition of these two functions, right? It's this function is being shoved into this one, and that's where you're getting r squared from. Okay, and so if you remember, anytime you take the derivative of a composition of two functions, you have to use the chain rule. Okay, so we're going to use the chain rule to find this, and the chain rule says you have to multiply the outer derivative times the inner derivative. Okay, but you can see the outer derivative here, right? If you just take the derivative of this, you get 2x. But remember, you have to evaluate this at the inner function. Okay, and the inner function is r of t. Okay, or just r. Okay, I'm not. There's too many parentheses here. I'm just going to write it as r. Okay, you're evaluating the derivative at the inner function, which is r, and notice you get 2r out, right? So it's sort of like you take the 2 down in front and you subtract 1. That's your outer derivative. So you get 2r for that's your outer derivative. Okay, and then you multiply that by the inner derivative. Okay, the inner function is r of t, and you're taking the derivative of that with respect to time, right? And so obviously that's going to be dr dt. That's your inner derivative. Okay, so using the chain rule, we know this derivative now, right? The derivative of r squared with respect to time is 2r dr dt. Okay, so I'm going to go ahead and distribute this pi to both terms. Okay, so you get pi h, and now times the derivative of r squared, and that's just 2r times dr dt. Okay, so now we have a relationship between dV dt and dH dt. By the way, it also involves dr dt. Okay, and so this is now, I guess, what you would say is our related rates. This is how they're related to each other in this equation. That's what this equation describes. Now, remember, we're evaluating this derivative when h is 20. Okay, so I'm going to evaluate this when the height is 20, which means everything in here has to be evaluated when h is 20. So I'm just going to rewrite this actually. Okay, so then you get pi, and now you run into r, right? What's r? Well, if you remember the problem, that's the radius of the little circular piece. And if you remember, we go back to it, they told us that the top of the cylindrical chamber has a radius of 2 centimeters, right? So that's this radius here. And so that little circular piece at the top, the radius of that little circle is 2, right? And it stays the same throughout the problem, right? It's constant. That doesn't change. That radius remains 2 as the piston moves downward. Okay? So going back to this, we know the radius is always 2 centimeters. That's constant. So when you get to this point here, what is r? Well, r is always 2 centimeters, no matter when, right? It's always 2. So I'm just going to plug 2 in for that. And then dH dt, we're evaluating that when the height is 20. So technically, we're going to evaluate this derivative when h is 20. So what is dH dt right when the height is 20, right? That's what this is asking. But we know it's always negative 5 centimeters per second. It's constant, right, throughout the entire problem. So in particular, when h is 20, it's still negative 5 centimeters per second. So this is still negative 5 centimeters per second. So I'm just going to plug negative 5 in for dH dt right when h is 20. Okay, now remember, we're evaluating this derivative right when the height is 20, technically. Okay, plus pi times the height, h. All right, well, h is 20, right? We're evaluating this at the moment when h is 20, so that's going to be 20. And then times 2, and then r is 2. And then dr dt. Okay, and again, we're going to evaluate dr dt right when h is 20. Okay, well, r is always 2. It's a constant. So when I take the derivative of it, I'm going to get 0. And that's going to be true at all points in time. In particular, it's still going to be true when h is 20. So this derivative is 0. Okay, and if you want to put units on this, it's going to be in centimeters per second, right? Radius over time, centimeters per second. Okay, so I'll plug 0 in for that. Okay, and that makes perfect sense. If the radius is not changing, which it's not, then the rate of change in the radius over time should be 0. Okay, so that just leaves us with, right, this cancels out, that's just 0. And so that just leaves us with 4 times negative 5, which is negative 20 times pi. Okay, and then let's put units on this. This is in, units of volume over time. So volume would be cubic centimeters over seconds, right? Because it's being measured, time is being measured in seconds. Okay, and if you plug this into your calculator, negative 20 pi is negative 62.83 if you round it off to 2 decimals. Okay, and so let's just double check our answer in MyMathLab. You can see they ask you to give the foundational equation, which is the volume of the cylinder. And then the related rates equation, which we found, right, to be this. And then finally, they want the rate of change in the volume of the cylinder right when the height is 20, and that's the negative 62.83 cubic centimeters per second. Okay, now one thing to take note of is what does this negative sign indicate? Well, that indicates that the volume is decreasing over time, right? That's what the negative indicates. If it were positive, it would be increasing, okay? But since it's negative, the rate of change in the volume over time means that it's decreasing. And obviously, the volume is decreasing over time. And so that's why there's a negative in front here. Okay, so hopefully you found this video helpful. And I'll continue to work some of the homework problems in Chapter 3. And hopefully you'll get a chance to look at some of those as well. Okay, bye-bye.